Hi, thank you for the introduction, and it's nice to be reminded of those times. Let's see. I'm assuming that everybody here was either here yesterday or is otherwise familiar with the definition of differential privacy. Let me know if that's incorrect, but here's a brief reminder. You need the notion of what it means for a pair of data sets to be adjacent. So data sets X and Y are adjacent if one is larger than the other and the smaller one is contained in the larger one, and the larger one has the data of just one more person. And differential privacy is not sort of binary. It isn't that something is or isn't differentially private. There's a parameter that caps the privacy loss. So our algorithms M are differentially private if for every output event, the probability that we observe this event when the database is X is at most e to the epsilon times the probability that we observe it when we are running on adjacent Y. And since the definition is symmetric in X and Y, the same inequality holds if you switch X and Y. Okay? And the probability space is over the coin flips of the algorithm. So yesterday, we saw the Laplace mechanism for answering a real valued query. And today, we're doing almost exactly the same thing, but we're looking at functions, queries, that map data sets now to some k-dimensional, so some vector of k-reals. Okay? And it should look really, really similar. What we did yesterday was we said, suppose we're looking at a function f, and we look at the maximum amount by which the data of one person can change the value of f. And we called that the sensitivity of the function, and we denoted it delta. We're just going to redefine delta now, appropriately for k, vector valued outputs. And so instead of just being the absolute value, the maximum absolute value between f of x minus f of y, it's just the L1 norm of f of x minus f of y. Any question? I saw some confusion.
Your slides are going a little faster.
Oh, thank you. I don't know what triggers that.
Yeah, it's very strange.
Yeah, okay. So anyway, so this is, so we're redefining the sensitivity. For the special case that k equals 1, this is exactly where we were yesterday. And the same algorithm works. What you do is, now that you have defined the sensitivity this new way, you add fresh draws from the Laplace with parameter sensitivity over epsilon to each of the k different outputs. I'm just pulling up a pointer. So independently to each of the k different outputs, you add this kind of noise. And again, you'll have differential privacy. And it is exactly the same proof. Only instead of having absolute values, we have L1 norms. But exactly the same proof. So this tells us a few things right away. First of all, if we fix, say, k arbitrary counting queries, how many people in the database like to play the violin? How many people in the database like to eat pasta? How many people in the database go jogging once a week or something like that? Okay, so k arbitrary counting queries. The presence or absence of any one person could potentially change the outcome to this sequence of questions by k, because you might have one more person who likes to jog and one more person who likes muffins, one more person who likes pasta, and so on. So, so the sensitivity for k arbitrary counting queries, known in advance, is k. And we have something really surprising for the second bullet. So think about contingency tables or histogram queries. So what do we mean by this? Imagine that you take your space of people and you partition it into an arbitrary number of cells. Let me call that k cells. So for example, you might partition people according to their annual income. People 0 to 15,000 a year. people from 15,000 to 30,000, 30,000 to 45,000, and so on. That is giving me a partitioning of the set of all people, and everybody is in one of these cells only, and no one is in more than one cell, okay? The sensitivity of a histogram query is just 1, because if we add or delete one person, we will change the count of only one cell, and we will change that count by at most 1. So delta in this case is just 1, even though it looks like k different queries. They are not k arbitrary queries. They are a partitioning. And that was the first real insight that we were actually onto something with differential privacy, that you could do something complex that was surprising, adding an amount of noise that looked more like 1 over epsilon instead of k over epsilon. Okay, now, good. So if you have k arbitrary counting queries and you want to be epsilon differentially private, then what this tells you is that you're going to need to add noise that is scaled to k over epsilon to each of the cell counts, to each of the counts, okay? There's another way of getting that answer. So that is to invoke what we call the composition theorem, which I alluded to yesterday, where I said that the epsilons add up. So suppose I want to ask 2 queries, and the epsilons add up, and I want a total epsilon of 0.2. Then what I could do is I could use an epsilon of 0.1 for each of the 2 queries, and they would add up to at most 0.2. So with that thinking, what we could do is we can, if we want to ask k queries, we can set some epsilon naught to be epsilon over k. We answer each of the queries with a privacy budget of epsilon naught. The k epsilon naughts at worst add up, giving us a total of epsilon loss, which is what we wanted. And again, we have noise that looks like k over epsilon for each of the individual queries. So 2 different ways of getting to the same place in this particular framework. Okay. Now, I've said that overly accurate answers to too many queries is disastrously non-private. Astonishingly, there are settings in which we can actually answer exponentially many counting queries. Not 2 to the n, but still something that's exponential in n. And this is like way beyond the scope of this talk, but I wanted to mention it here. One issue with this is that the computational costs of doing these very, very demanding things is very high. And that turns out to be inherent. There's no way around that. Why so much focus on counting queries? I should comment. First of all, because we can. Like, we understand counting queries pretty well. Secondly, many of you are aware that almost everything that you can do in the PAC learning model, the probably approximately correct learning model, you can also do in Kearns's statistical queries learning model. And statistical queries is basically just counting queries. So it's a very powerful framework that lets us do complicated things with a sequence of counting queries. Good. Okay, so we've been talking about adding Laplace noise. And a natural question that people often ask is, what about adding Gaussian noise? Gaussian noise is so nice, it's so symmetric, it's beautiful, we understand it really well. What about Gaussian noise? And Gaussian noise basically fails in the tails. That is to say, differential privacy requires this bounded ratio condition. And if we add Gaussian noise way out in the tails, we will not have the bounded ratio condition ever. So the absolute value of the ln of these things is not bounded by any finite epsilon as x goes off to infinity. Okay? So there's a technical condition that is failing us here. And that motivated the first relaxation of differential privacy, which is called epsilon delta differential privacy. A lot of the literature is on epsilon delta differential privacy. The definition looks really, really similar to what we had before, only we have this additive plus delta term. So that means that the definition you had before was just delta equals 0, special case. And that's often called pure differential privacy in the literature. So, right, so that's the definition of epsilon delta differential privacy. Now, there are two kinds of deltas in the world. One kind is the so-called death and destruction delta, which says that with some small probability, anything goes. Privacy loss could be infinite. There are really nice reasons to do something like this. And if there's time later, ask me about them. But that's not where our focus is going to be for the rest of today. For the rest of today, we're looking at a graceful degradation that I alluded to yesterday. This actually happens with Gaussian noise. If you add Gaussian noise with the right variance, then sort of with high probability, your privacy loss will be bounded by epsilon. But if that fails, you're still really likely to be bounded by 2 epsilon. And if that fails, you're still really, really, really likely to be bounded by 3 epsilon and so on. So that's a graceful degradation. You can't really talk about expected privacy loss in the first case. You can talk about expected privacy loss in the second case. So what's the right setting of the parameters for the Gaussian? Here it's described for for arbitrary k, you can think about k is equal to 1. But the key point here is that we're going to, actually don't think about k equal 1, think about arbitrary k. We're going to redefine sensitivity one more time. This time, instead of having the L1 norm of f of x minus f of y, we have the L2 norm, which is smaller, which looks more like square root of k sometimes instead of k. So it turns out that if you set the variance to be sigma squared delta over epsilon squared with this definition of delta, then you get epsilon delta differential privacy whenever that constant c is at least 2 times the log of 2 over delta. So you have to kind of puff things up a little bit. Look at the k equals 1 case. The k equals 1 case, a single counting query, the sensitivity again is 1. And we would like to be adding noise that is scaled to the standard deviation should be 1 over epsilon, like it was before in the Laplace mechanism. But we don't quite get that. We have to puff it up by this log of 1 over delta term, which is annoying. Nonetheless, what this gives us is that for k arbitrary counting queries, since the L2 sensitivity is square root of k, for k arbitrary counting queries, we end up adding noise that looks like square root of k, that's the sensitivity, times 1 over epsilon, times this square root of 2 log 2 over delta. So compare that to what we had with the Laplace mechanism, which was giving us pure differential privacy. That had a delta of 0. It doesn't make sense to plug that into here, but that had its own bound, k times 1 over epsilon. So at the cost of this log of 1 over delta term, we go from k down to square root of k. Okay? All right. Now, let me introduce the formal privacy loss random variable. suppose I have two adjacent databases, X and Y. Let's fix X and Y. And I have an algorithm M, and I'm running M on X, not on Y. It really matters. This is not a symmetric definition. I'm running M on X, and I pull an outcome accordingly, Xi. So the privacy loss of Xi when I'm running on X with respect to this adjacent database Y is the log of the probability, or the probability density if it's continuous, of observing Xi when the database is X over probability of observing Xi when the database is Y. So in epsilon differential privacy, pure differential privacy, the privacy loss is guaranteed always to be bounded by epsilon, never worse. In epsilon delta differential privacy, it's morally telling us that with probability at least 1 minus delta, the privacy loss will be bounded by epsilon. So most of the time, you're in good shape and you're not giving big hints as to which database you're actually working from, X or Y. Now, recall that, as we discussed yesterday, privacy loss can be either positive or negative. It's positive when we're running on X if we see a value that is more likely under X than under Y. It's negative when we are running on X if we see an outcome that is more likely under Y than it is under X. So when you have large degrees of composition, you can have cancellation, and you're very, very likely to see cancellation. And that gives us what's called the advanced composition theorem. So let's take a look at what it says. We have two parameters, epsilon naught and delta. And the reason I'm calling it epsilon naught is because I want to look at the composition of many algorithms, each of which is epsilon naught delta differentially private, and I want to see what is the epsilon we get as a result, operating on things that have a base level of epsilon naught. Okay? So what this says is this should be for all delta greater than 0 simultaneously. So if we are composing a bunch of pure differentially private algorithms, what we get is the following. We get an algorithm whose epsilon loss is k epsilon naught squared plus basically a log 1 over delta term times epsilon naught, and then a delta. So this is for all delta simultaneously. So if I want a smaller delta here, I get a bigger term in here. They have this continuous sort of trade-off. Okay. Now, one way of thinking about that is that the probability, so okay, epsilon naught, think of epsilon naught as something less than 1. Epsilon naught squared is even smaller. And so what we're going to end up with is a situation where the k epsilon naught squared is not our concern, that our concern is going to be this term, the sort of square root of k log 1 over delta times epsilon naught. Okay? You can just, yeah, all right. So what this says is that the probability of the privacy loss exceeding t times square root of k times epsilon naught is falling exponentially as in t squared with some constant there, like 2 or 4. All right. And what that suggests is if you want your cumulative loss to look something like, to look like epsilon delta overall, you set epsilon naught to be approximately epsilon over square root of 2k log 1 over delta. When you do that, this denominator cancels here. And you just get your epsilon. Okay? By the way, I've been talking about composition of pure differentially private algorithms. A similar statement holds if I'm looking at the k-fold composition of epsilon naught comma delta prime differentially private algorithms. So the intuition for what's going on is the same. It turns out that the proof is quite a bit more subtle for that case, and we're just going to ignore it today. But for the pure differential privacy case, the composition of pure differentially private algorithms, the proof is fairly straightforward. So the first step is to argue that the expected loss when you're running an epsilon naught differentially private algorithm is at most epsilon naught squared. And we had a 2 epsilon naught squared that was improved by Kairuzo and Viswanath to get rid of the 2, and then there are a few other proofs that have come along since then that also get rid of the 2. So the expected loss is at most epsilon squared. And this is where we're going to end up with our k epsilon naught squared sort of in expectation. Okay. Then we have the fact that because these are epsilon naught differentially private algorithms, the privacy loss is always going to be bounded by epsilon naught. Doesn't matter what the history was, how people decided which algorithm to run, even which databases to run them on, doesn't make any difference. At each step, the sort of additional loss is always bounded by epsilon naught. And so now we're in a situation where we can apply the Azuma-Hufting bounds. We have a bound on the expectation, we have an absolute bound, and we put them together and we get something of this form. So the surprising part in some sense is the fact that even though the privacy losses are not independent at subsequent rounds, you can always invoke the bound on the absolute privacy loss given by pure differential privacy. Okay. So let's go back to this statement. We're composing a bunch of differentially private algorithms. And as I indicated, the same statement is essentially true whether we're talking about approximate differential privacy or pure differential privacy. And to get an overall epsilon, we set epsilon naught to have this form. So you might ask, why be so restrictive? So we're forcing the epsilon naught to be very small so that we can apply the composition and have a union bound and know that, our chance of exceeding of blowing things is bounded by delta. So we're pushing things down very hard so that we can apply the composition theorem. But all we really care about is the cumulative privacy loss. And so it may be that along the way, when we have multiple executions, multiple differentially private algorithms that we're applying, we can afford to have some larger multiples of epsilon naught. Maybe occasionally we'll have a 2 epsilon naught or a 3 epsilon naught, and sometimes we'll have a -4 epsilon naught or a -2 epsilon naught. So all we care about is cancellation in the long run. We don't need to control each step so tightly. And so that asks the question, when or how or can we get rid of that nasty, log 1 over delta. Forget about the square root of 2. You can't get rid of the square root of k. Just that's a typo. But when can we get rid of the log 1 over delta term? That's the question. Okay. So that gave rise to the next relaxation of differential privacy, which was, we called it concentrated differential privacy. You'll see why it was subsequently renamed as mu-CDP. And informally, concentrated differential privacy says that the privacy loss random variable is sub-Gaussian. That's the only condition. So it turns out that if you study the Gaussian mechanism is, has this property. The privacy loss random variable is sub-Gaussian. The probability that you're going to have a privacy loss of k times epsilon turns out to be bounded by e to the minus k squared over 2. So it is all by itself sub-Gaussian. So, sorry, forget this part for a second. Now, let's just look at this piece over here. What happens under composition? The sum of sub-Gaussians that have standards of tau 1 up to tau k is itself sub-Gaussian with a standard of square root of the sum of the squares. Okay. So this gives us exactly the composition theorem that we want. No log 1 over delta term, no delta showing up whatsoever. And it just works. Now, our version of concentrated differential privacy wasn't closed under post-processing. Privacy loss didn't get worse under post-processing, but it didn't keep its nice form. It didn't stay concentrated properly. And that was fixed, improved on by Bunn and Steinke, who gave a definition which is very, very similar in spirit. Again, it's saying that the privacy loss is sub-Gaussian. They do it in terms of Rényi divergences. We needed this to be true for all alpha. They need it to be true for all alpha in the range of 1 to infinity. Okay? This, too, holds for the Gaussian mechanism. It holds for the Gaussian mechanism because it's a relaxation of mu-CDP, and mu-CDP held for the Gaussian. And this is the version of differential privacy that was used in the US 2020 decennial data for the redistricting data. Okay. Good. So we're about halfway through the talk. We talked about 2 relaxations, epsilon delta differential privacy and concentrated differential privacy. And there are 2 further relaxations that are very much worthy of note. One of them is called alpha Rényi differential privacy. It is actually a relaxation of concentrated differential privacy. Alpha and epsilon are fixed parameters, and this is the requirement that the Rényi divergence be bounded by epsilon for all divergences up to alpha. Compare that to this condition which CDP had, this bound that CDP had. And the other is so-called truncated CDP. And truncated CDP is designed for something called amplification by sampling, which you haven't seen yet, but you will see on the next slide. But that's all I'm going to say about it. So now we're going to talk about amplification techniques, a couple of those, and if there's time, a few words about adaptive data analysis. So, amplification by subsampling. Suppose we have a pure differentially private algorithm. What I'm saying also has a life in the epsilon delta world, but let's just focus on pure. So my algorithm maps data sets to some range. Now consider the following modification of the algorithm. For each element in my data set, independently, I'm going to flip a coin that has probability alpha of coming up heads. If it's heads, I include xi in a new data set that I'm building. And if it's tails, I don't include xi. So when I've done this, when I've finished with all of this, my new data set is called Z. It's just a subset of the original data set, where membership was obtained by this Bernoulli process. And now I run my original algorithm, not on X, but on this subset of X that I've selected, Z. So is the algorithm clear? Choose a random subset, apply your algorithm to the subset. The theorem says that the resulting algorithm, instead of being alpha differentially private, is alpha times e to the epsilon minus 1. So when epsilon is small, that's about epsilon. Okay, just a little bit bigger than epsilon. So the resulting algorithm is, at worst, 2 alpha epsilon differentially private. Epsilon is less than 1. This is a win. I didn't increase the noise that I'm adding if it was a noise algorithm. Not all differentially private algorithms add noise. Some of them do other things. But I am working on a smaller data set. Okay, so the intuition for why we gain some mileage here is that one only suffers, this is just intuition, there's something not rigorous in what I'm saying, but one only suffers privacy loss if one is retained and put into the data set Z. That's the intuition. And that turns out to be just about right, but you have to do a little bit of work to make it clean. Moreover, the privacy that's afforded depends on secrecy of the sample. It should not be known who makes up data set Z. Okay. So here's a really compelling application of amplification by subsampling. You're all familiar with gradient descent, right? Good. So my loss function has to be Lipschitz for this discussion, and it's projected gradient descent. We're going to work over some convex set C. So we've got our learning rate, we add, and then we project down, okay? Good, so that's projected gradient descent. You all know it, and you're all familiar, I think, of the case where the loss function is just, it's the sum of the losses for each of the individual xi's. So here is a variant. I haven't used amplification by subsampling yet. This is private gradient descent, privacy-preserving gradient descent. We're going to choose a noise variance. It has to be chosen appropriately. I'll show you on the next slide what it is, but that's not the focus of the discussion. The rest looks pretty much the same except for one thing. When I'm computing the derivative of the loss for individual xi, I'm going to add a little bit of Gaussian noise to maintain the privacy of xi in the computation. So my noise has to be, scaled the right way in order to guarantee that I'm going to have privacy. And we're doing this, right, okay. Good. So this gets optimized as follows. This was our core statement. So we're summing up this terms over all of the xi's. And we're adding noise every time. We're going to replace that step as follows. Choose a random element, Z, in the data set. So Z is chosen uniformly from x1 up to xn. Now, I put in the derivative of the loss function with respect to Z here, and I multiply the quantity by n. So let's look at that. First of all, before I was summing these terms up over x1 up to xn. Now I'm just taking one term, but I'm multiplying it by n. So the scale is right. It's the same scale as before. But what happened to my computation costs? Oh, and the expectation is the same. Now, what happened to my computation costs? They plummeted by a factor of n. So that's great. But there's this fear, right? I took something which was a function of just one element, and I multiplied it by n. So the sensitivity went way up. That's bad. That's going to cost me a factor of n. However, I have privacy of the subsample. That lets me divide by n. And so the privacy is maintained, the scale stays the same, the expectation stays the same, the computational costs improved dramatically. And when you run for n squared steps, you get the desired expected excess risk bounds. And this is the value of sigma squared. So that was 2014. There's been a tremendous amount of work on differentially private gradient descent because it's so important and so pervasive in machine learning and machine learning under large data sets. And there are lots and lots of different variants of it, you know, with mini batches and so on and so forth. The latest and greatest is really beautiful, but it doesn't wildly improve on the bounds that are given here. So it's very interesting. Okay, so that was our first amplification technique, amplification by subsampling. The next is amplification by shuffling. So let's take a step back and look at a really old algorithm due to Stanley Warner. So this was designed to allow people to answer surveys in a way that, surveys about embarrassing or illegal activities in a way that provided some deniability. But I've made it just a little bit more general. So the way it works is this. We have an individual who has a data point which is 0 or 1, like do they floss regularly or not? And we have a probability p. So we flip a coin that has probability p of coming up heads. That's B. If the coin is heads, then the person answers randomly, and otherwise they answer truthfully. Okay? So we have deniability. If I say I don't floss, I have deniability because, for all you know, my Bernoulli came up heads and I'm just flipping randomly. And a very, very simple case analysis shows that this will give epsilon differentially private if the probability of answering randomly is large enough, at least 2 over 1 plus epsilon. And notice that here we're assuming that the respondent can actually carry out this computation and then just hand the results to the data collector with no anonymity. You know that it's me, but you don't know whether I randomized or not, and so I have deniability. Okay? Now, it's pretty easy to estimate from this the fraction of true ones in the collected ones, because you know that with high probability about p times n over 2 of the ones that you observe came from the randomness. So you can estimate the approximate fraction of ones, and you can multiply by n to get an approximate count rather than fraction of ones. And the noise will look something like square root of n over epsilon. Okay. In the Laplace, it was looking like 1 over epsilon. In the Gaussian, for a single query, it was like square root log 1 over delta over epsilon. Okay? So this is clearly much worse, but there's no anonymity. Okay. Industry loves randomized response. I told you that it was differential privacy is being used in many different settings, many different contexts. Google, Microsoft, Apple, they're all using randomized response. Okay. Why do they like it? One reason they like it in industry parlance is that the trust barrier, in their words, has been moved to the client. In other words, don't blame us for anything that happens or any data breaches because it doesn't matter because everything was made private before we got it in the first place. So that's really nice. But there's that cost of that square root of n, that's expensive. So another issue is, remember I said yesterday, nothing is ever done just once, that composition is pervasive, it's the name of the game, it's everything. So we're being measured and measured and measured and measured and measured constantly, maybe multiple times a day. And so the cumulative losses could add up significantly. Right? So the idea of the shuffler is it's just, I think currently it's just an idea. I don't know that this is being implemented. But imagine that when people submit their various randomized responses, and randomized response is much more general than just counting queries. We're not going into all the things you can do with it. Imagine that somewhere in the network was a trustworthy and trusted component that just shook all of the pieces and permuted them randomly, so that it was completely unknown which randomized response came from whom. So you're breaking the tie between the person who sends the response and the actual response. Okay, just the opposite of what I emphasized we had in Warner's method. So suppose you had such a shuffler. Now, there's a really, the idea of introducing the shuffler came from this very interesting, thought-provoking and thoughtful paper by Bittau et al. And one of the things that they argue, they think a lot about how you might implement differential privacy and even gradient descent in a big network. And they point out that by observing network traffic, you can't really hope to have privacy of the subsample, like who was involved in the subsample. Can't be maintained, kept private. So very thought-provoking and made more rigorous in a pair of papers. One of them is Chu et al. And I want to talk about a specific slight change in the way to think about randomized response once you have a shuffler. So in the algorithm that they present in their paper, and again, they present a lot of algorithms, but I'm focusing on this counting of single bits because we've been able to pull that through the talk. So we're going to run randomized response, but instead of having a chunky probability of randomizing, your probability of randomizing is going to be pretty small. A little bit bigger than 1 over n. Maybe some log 1 over delta term times some constant times 1 over n. Something like that. So what happens is, first of all, when everybody independently flips that very low bias coin to decide whether they're going to be a noisemaker or not, a small number will be noisemakers, and the rest will be answering truthfully. But remember, the answers are all going to be shuffled up, so we don't know who's answering truthfully. We don't know anything about tying anything to anybody. Okay, so let H be our set of randomizers. These guys, they flip coins that have probability a half of coming up heads. So they're creating the noise. When we add up all the answers, their noise is distributed as a binomial on size of H people with probability a half, right? So even for nearly constant expected size of H, we're going to get some nice privacy with very low noise. We'll get, remember, H is really quite small. And it has to be big enough to sort of give us something that's at least 1 over epsilon in expectation. But that's pretty small. So even for sort of nearly constant H's, size H's, we're going to get nice privacy with low noise. Now, our argument about why randomized response was private did not involve privacy of the subsample. There was no subsampling. There was kind of implicit subsampling, but the algorithm that was being applied, if you got subsampled, was tell the truth. That is not differentially private for any finite epsilon. So we're not applying privacy of the subsample. Here, in this construction, you actually can get a little bit of privacy of the subsample too, because, or amplification by subsampling, because participating in the case where you actually give your real data rather than being a randomizer, that happens with probability less than 1. So you can even leverage a little bit of extra privacy from that. So that was a special case. And a more general statement is of the following form. This is by Erlingson et al. And it says that, well, for epsilon less than a half and delta, the local, and I didn't really get into all the rich things that could be done, but you saw an example of locally randomizing, and if the local randomizer is epsilon differentially private, then the shuffled algorithm yields these kinds of bounds. Look at that n in the denominator. Yes, it's a square root of n, but when you're looking at things that are internet scale, that square root of n is really large. So it says that by shuffling, you can substantially improve on what you could do just with randomized response on its own. Again, I don't know that shufflers have been built and who would build them and so on, but this direction has received quite a bit of attention. Okay. I'm going to briefly mention a third approach for amplifying privacy. And I'm going to do it just by building a little bit of intuition. So I've seen two names for it. There's a paper called Amplification by Iteration, so we'll use that name. But you could also think of it as amplification by secrecy of the journey. So let's go back to our noisy stochastic gradient descent. And we're going to look at a version of this in which at every iteration, just one element is processed. That's not what, yeah, okay. Now, and assume that the order of the elements is not secret. This is going back to that point about you will observe traffic in the network, so you can't really hide who is participating at what time. So imagine that we do something like this. We take, I'm just going to think about just 2 steps of this little specialized noisy stochastic gradient descent algorithm. First, we take a gradient step using the first element, x1. No secret who x1 is, okay? And instead of adding all the noise that we actually need in order to maintain proper privacy for x1, we're going to add half the noise that we would need. We're scaling the noise, dividing the scale by a factor of 2. Okay? Then we take a gradient step using, sorry, I said scale the noise, we're scaling the variance. Then we take a gradient step using x2. Again, no secret about x2. And again, we add noise scaled to half the variance that we would need for protecting x2. But look at the world from the perspective of the data point x1. Everything, so from the data point x1, there have been 2 noises added. And the sums of their variances is sigma squared, which was enough to give it privacy in the first place. So even though they didn't happen, it didn't all happen at once, the kind of total noise after x1 got involved is the right amount. And one thing that we did that was really important, we did not publish the result after we added that sort of half noise. we kept that secret. And so x1 possibly is completely protected. And that's the intuition in iteration by privacy amplification by iteration. By iterating and doing stuff after we dealt with x1, x1 is getting the benefit of all the noises that were added after it was involved. Now, if we were to stop here, x2 would be out of luck, right? Because we've only added noise scale to, the variance is only half what it should have been for x2. And that's a real problem. So x1 is fully protected, but x2 is sort of only half protected. Okay. So the bottom line is, this actually works. And I have no idea. I worked on my animation, but we didn't get the right name. So first paper of Feldman et al., this one. They showed that this works. And they discussed techniques for dealing with the lack of privacy for the guys that are processed toward the end of the chain, x2 in our example. And one of the things that they do is they just continue processing using publicly available data that's just hanging around or scraped off the web. And that's one technique. They have other techniques. Now, what would happen if we took more steps, if we wanted to go, say, up to n squared steps, which can be really useful? Well, two different proof techniques have been shown to, have been used to argue that the privacy loss actually levels off as the number of iterations goes to infinity, even though you have to keep adding, like, you'll keep hitting the same people over and over again. Really beautiful work. And that's in these papers. Both analyses use the Rényi differential privacy that I mentioned earlier. Okay. So I don't know if I should talk for an hour or if I should stop, because I have a couple more slides on the last topic. Your call.
Well, you let people leave now or leave.
Yeah.
Keep on talking.
Okay, so the very, very last topic is how do we use differential privacy for adaptive data analysis? You've probably all seen papers like this one, why most published research findings are false. And it's all about p-hacking, or like doing things until you get the answer you want and publishing that. So the issue is adaptivity. It's having your there are two issues. One is that you may just have too many hypotheses, and that's that. But the other issue is when you choose your subsequent queries as a function of the outcomes that you saw before. And that will get you to p-hacking faster. So even in gradient descent, we saw that kind of the second step depends on the first step. Like, exactly where we're computing the gradients depends on what happened in the first step, and so on and so forth. And more insidiously, studies that are conducted by researchers who have read papers and then used the same data set to do follow-up studies, those are also adaptive. And the take-home message here is that differential privacy addresses the issues that arise strictly due to adaptivity. So let me give you some intuition for why this is the case. Let's fix a query. Say, what fraction of the population is over 6 feet tall? This is a fixed query. In proper methodology, what I should do is, once I know what I want to ask about, I then go off and I recruit a data set, and then I test my hypothesis on this recruited data set. So since this is the first query, there's no opportunity for adaptivity. And we know that almost all large data sets will give an approximately correct response to this. Like, it'll tell me something about what fraction of the population if the sample is chosen properly and is large enough. And this is true whether the sample was chosen before I asked the question or after I asked the question, as long as they're independent. Okay. The way I think about this is, for a given query, most data sets that I could collect, are representative of the underlying population with respect to this query. There could be some super weird data sets, like if I only chose the people over 6 feet tall, then I'd get a very different answer. But if I chose a random data set, that isn't what would happen. Most of the data sets have this nice property. So suppose in the process of adaptively exploring, the analyst finds a query for which the data set is no longer representative of the population. We know that for the first query it will be. But suppose she finds a query for which the data set is not representative. Since that is so unlikely to have happened with an independently chosen data set, it means that she probably learned something very significant about the data set. And that's how she was able to create that query that had that property. So in an intuitive sense, preserving the privacy of the data will provably prevent overfitting. And that intuition is correct. Now, what does that say? It says interact with your data set in a differentially private way. And as we discussed yesterday, for most people who work with data, the answer is absolutely not. I don't know how. I don't want to learn how. It's too hard. The techniques I need may not even exist yet. What can we do? So, and this is my last slide, we propose that you use something called a reusable holdout set. So the idea is take the data, partition it into a holdout set and a training set. Give the data analyst, you, unrestricted access to the training set. We're not interested in privacy. We want to use differential privacy to do something for us. So let people interact with the training set exactly the way they would have interacted with the training set in general. But whenever they think they have learned something really interesting, then in a differentially private way, test that on the holdout set. Because we interact with the holdout set in a differentially private way, it sort of remains independent of what's happening over here. Subsequent training doesn't depend very much on the holdout set. It's essentially independent. And so the holdout set can be reused. Normally, once you've used a holdout set, that's it, it's over. Everything you do afterwards depends on the holdout set. But here, by interacting with it in a differentially private way, when you find something interesting that you want to check, you can still reuse it later for later interesting things that you find that you'd like to check. Thank you.
Okay, are there any questions?
Yeah.
This is like a very wild thing, but regarding like the thing about the subsampling.
Sorry, regarding what?
Oh, yeah, regarding the subsampling
Yes.
with the like gradient descent. One thing I was wondering was like, how does the like amount of noise you have to add change? Because like normally when you have like the sum of the xi's, you only have to add like one noise total. But if you have like a like n times something, doesn't the noise that you have to add like blow up?
The noise, okay. So you mean in the unoptimized version, yes? Before,
I'm not sure.
so this is the unoptimized version where,
Yeah, that.
right.
And then you say that you replace the sum of the i's with like n times a single one, and then you have to add some noise on top of that.
Right.
But doesn't the noise you have to add there, doesn't that noise have to be like even bigger than before?
Yes. Sorry. No. The reason that we don't have to is because we get to, so the sensitivity increased, which would make you think you have to add a whole lot more noise, but you don't, because the privacy cost decreased by almost the same amount.
Okay, so do they cancel out?
They cancel out.
Okay.
They cancel out, they leave a factor of 2, I
Okay,
think.
so basically the main thing is that it's much faster, but the
Right.
the amount of noise that's added is.
It's much faster because at each iteration, you only are dealing with one sample instead of n samples. Yeah. Mhm. Right. It was a good question. Yeah.
Could you speak more about the reusable holdout set? Like, what's the size of the training versus holdout groups? And also, how do you enforce that you interact with the holdout in a differentiable, private way?
So the way to good. All right. Sorry, I'm looking for my slide. It's way at the end. Okay. So first of all, to enforce that the interaction with the holdout set is done in a differentially private way can be like, if you're the data set owner, then you may require, for example, that somebody use algorithms from a known differentially private library, or that they present a proof that the algorithm is differentially private, that they want to use. There are, by the way, starting to be several libraries for differentially private data analysis, including the OpenDP project at Harvard. So, you know, there's a collection of things that you can use, and their bounds are known, and so on and so forth. And the implementations are there. Okay. So that kind of gives you an answer to the enforcement question. If you have collected the data and you simply want to protect yourself against overfitting due to adaptivity, you might, you know, enforce this yourself on your own data, the data that you've collected. The second question was, how large does the holdout set have to be? So the size of the holdout set depends in part on, so I mean, there are various parameters. It doesn't have to be anywhere near so large as we expect the training data set to be, but it has to be large enough that you should get reasonably good estimates for the kinds of things that you want to be checking. So you have to look at what the algorithms require, the different differentially private algorithms require. Yeah. Are there any limits to how much privacy you can get? Is that the question?
Yeah, basically.
Great. So are you saying, can we get epsilon equals 0? No privacy loss? Absolutely. Don't answer anything. I don't mean to be facetious. I do want to point out, though, that you can always do that. Now, there is a cost. The cost often will look like 1 over epsilon, like for counting queries, for example. And you can't get away from that epsilon in the denominator. So the smaller you make epsilon, the more noise you're asking per query. Notice something, though. 1 over epsilon is completely independent of the size of your data set. So one thing that I meant to say was that even in introducing differential privacy, it is a definition of privacy that was tailored to the statistical analysis of large data sets. It turns out to provide utility for data sets much smaller than what we imagined would be the case. The techniques turned out to be useful even for much smaller data sets. So if epsilon is really small, 1 over epsilon or k over epsilon or square root of k over epsilon, those may not be very large compared to n. If your data set really is small, then of course hiding the presence or absence of one or a couple of people means you're going to destroy utility. Take the special case when the data set has just one person in it. We still want to be sure that it's differentially private. You're going to destroy the answers, and that's intentional. If you completely change your population, swap out all of the Republicans for Democrats, you'll get different statistics, and you're supposed to get different statistics. So does that help answer your question?
Yeah, I guess I was thinking of like a more quantitative bound. Like,
Sorry?
I was thinking of more of like a quantitative bound. Like there's like it feels of like a Heisenberg critical situation where you have like maybe the product of utility and privacy is some.
I'm sorry, I just can't hear you.
I'm imagining a situation where you have like a bound on like how much privacy like and also how much utility you can. Like it feels like a really abstract question.
Well, is there always a privacy utility trade-off for any given query? For any given mechanism, there will be. Are there lower bounds? Yeah, there are some lower bounds that are known, absolutely. Yeah. So I can point you to some papers that have exactly that sort of thing. Yes. And in fact, no, let me just leave it as yes, and I can point you to papers. Mm-hmm.
Following up on what you just commented on there, do you have any figures in mind for how small you've seen meaningful results come on for data set sizes, I mean, for applications of DP?
Like what size data sets are the smallest that are needed?
Like you've seen data, DP applied to some data sets. Do you have an idea of how small we're talking?
I don't trust myself to answer that question. I've seen numbers, and I think I remember some, but I am so not a practitioner that I could be off by an order of magnitude and embarrass myself terribly. So,
How recent those results were then, maybe?
hmm?
How recent those results on small sizes came out?
So I think people have looked at stuff like that sort of continuously. Yeah, right. Mhm. One place to look, by the way, is in the statistics literature, like less than in the computer science, but more in the statistics, because they tend to be very, very interested in finite sample stuff. Yeah. Yes.
So for this differential privacy application, usually epsilon is not like a negligible quantity. So there's like an upper bound on how many queries the analyst can make. So assuming that the bound is actually achieved, like what will happen? We will just stop answering
Great.
everything.
So if I understand the question, so here's how I think about it. As the data administrator or the person who is responsible for the privacy of the data, I might choose some upper bound epsilon that I'm willing to allow anybody's data to be exposed to. So one way of handling that is we keep track of the cumulative privacy loss using any of the various tools that we have, or the composition mechanisms, or different parameters for different kinds of things, variants of differential privacy. But we keep track of them, and when we reach the cumulative limit, we say, that's it, the data set is closed. No more. By the way, people are just horrified when they hear this idea, but nonetheless, that would be a privacy-centric view of how to proceed. Of course, there are other things you can do. I'll give you an extreme example. Let's say, for concreteness, that you want a cumulative epsilon of 1. So answer the first query with a privacy loss budget of 1/2, the second one with a privacy loss budget of 1/4, an 1/8, and so on and so forth. So you can answer for a long time. Eventually, your answers aren't telling anything, but you're not violating the bounds. Interestingly, sometimes very, very, very large noises turn out to still be useful. And I can point you to an amazing paper that has a result about that. Yeah. But you can't go forever. And that's related to this fundamental law of information reconstruction, which says overly accurate answers of too many queries is blatantly non-private. So eventually your too many will overwhelm whatever accuracy you're insisting on, and you'd be done.
Okay, so if there are no more questions, thank you again.
Thank you.
The dominant final thought in the series is not marked.